When we think of the infrastructure powering modern civilization, we tend to picture steel grids, fossil fuels, and thousands of miles of fiber optic cable. But the engine keeping terrestrial life running doesn't rely on electricity or code. It runs on the precise, rhythmic movement of trillions of winged insects. Globally, the clade Anthiphila boasts over 20,000 distinct bee species. Together, they function as the primary distributors of genetic material for 75% of our agricultural crop types, from the coffee we drink to the alfalfa that feeds livestock. This diagram maps the ecological network tied to those pollinators. If that central pollinator node drops out, it triggers a mathematical failure across the board. Wild plant reproduction drops off a cliff. Without those seeds and fruits, small mammal and bird populations crash, starving the apex predators relying on them. Within human systems, the fallout is a matter of nutrition. While staples like wheat and corn rely on wind, the fruits, vegetables, and nuts providing our essential micronutrients depend on insects. Without these pollinators, global yields of nutrient-dense crops plunge. Epidemiological models project this would leave over 70 million people newly deficient in vitamin A deficit that leads directly to ocular disease and blindness. Bees act as a load-bearing, invisible workforce, sustaining the structural integrity of life on Earth. To see how this workforce operates, we must look at the physics of a single flight. As a bee flies through the air, aerodynamic friction generates a slight positive electrostatic charge across its body hairs. Flowers are grounded to the earth, so they generally hold a negative charge. When the bee lands, that electrical gradient causes the negatively charged pollen grains to leap across the air gap and snap onto the bee's body. Once coated in this dust, species like honeybees and bumblebees, known as corbiculate bees, must consolidate the payload for the flight home. They scrape the pollen down to their hind legs, utilizing a biomechanical hinge called a pollen press. By repeatedly bending and straightening the leg, they hydraulically force the loose powder into tight aerodynamic pellets. Some plants, like tomatoes and eggplants, lock their pollen tight inside closed tubes. Honeybees are physically incapable of accessing it. These plants rely on the sheer mass of wild bumblebees, who grasp the flower and vibrate their thoracic flight muscles at highly specific frequencies to shake the pollen loose, a mechanism known as buzz pollination. While bumblebees form small annual nests, eusocial honeybees operate at a completely different scale. A hive of up to 100,000 individuals functions as a single superorganism. It makes complex logistical decisions with the decentralized computational power of a neural network, operating without a central leader. Instead, internal labor is regulated by a mechanism known as the common stomach. If the colony experiences a sudden protein deficit, that chemical lack of saturation ripples through the workforce. It triggers a mathematical algorithm that dynamically accelerates the maturation of young nurse bees, sending them out of the hive as foragers to offset a shortage. This illustrates the waggle dance, the colony's method for communicating where to find resources. A scout performs a figure-8 run on the comb. The angle of the straight waggle run gives the exact directional vector relative to the sun, and the duration dictates the distance. To get the attention of resting foragers in total darkness, the dancer vibrates the comb and releases a specific chemical scent cocktail. Over 120 million years, evolutionary pressure has refined these organisms into a distributed biological intelligence that rivals modern human supply chains. Despite their efficiency, global bee populations are in decline. Public discourse often points to a single mysterious threat, but colonies are collapsing under the compounding weight of multiple human-made stressors that overwhelm their resilience. The first major stressor is habitat loss, driven by modern agriculture. We've replaced diverse wildflower meadows with massive, unbroken crop monocultures. For a few weeks, a blooming almond orchard provides an intense surge of nectar, but once the bloom ends, the landscape turns into a nutritional desert, leaving the bees malnourished. On top of starvation, foraging bees also face exposure to synthetic chemicals. Systemic neonicotinoid pesticides permeate the entire plant, including the pollen. These are neurotoxins. Even sublethal doses impair the navigational memory a bee needs to return to its nest, driving high mortality rates across both wild and managed populations. Climate change acts as a threat multiplier. Bees are ectothermic, meaning they have strict physiological limits dictated by their environment. When heat waves push ambient air temperatures past 45 degrees Celsius, resting bees breach their critical thermal maximum. They can no longer manage the energetic costs of flight and thermoregulation, succumbing to rapid desiccation. Inside the hive, the situation is worsened by global trade, which introduced the Varroa destructor mite. These invasive parasites clamp onto developing pupae to feed on their fat bodies. In the process, they act as efficient vectors, injecting lethal viral payloads like deformed wing virus directly into the colony. When you combine malnutrition, neurotoxins, extreme heat, and viral epidemics, you get a multi-dimensional collapse. The localized loss of these insects threatens to destabilize international commodity markets and hollow out global food security. Faced with this crisis, a popular assumption is that we can engineer our way out of it. We see patents for robotic microdrones designed to artificially pollinate crops, promising a technological replacement if the biological vectors fail. But robotic pollination ignores the 85% of all terrestrial wild plants that require diverse animal pollinators to survive. Attempting to replace the free natural capital of trillions of insects with paid manual labor and machines would cost hundreds of billions of dollars a year, rendering large segments of agriculture financially unviable. The realistic solution is deploying our most advanced technology to protect the biological infrastructure we already have. At the genetic level, researchers have successfully bred a strain of honeybee exhibiting Varroa-sensitive hygiene. These bees possess the olfactory capability to smell mite-infested pupae hidden beneath wax cappings. They uncap the cells and physically expel the parasites, interrupting the mite's reproductive cycle without the use of toxic chemical treatments. Physical apiary management is also shifting towards precision agriculture. Commercial beekeepers are integrating electronic beehive monitoring systems. These smart hives use internal telemetry to continuously track microclimates, gas levels, and specific acoustic signatures, alerting managers to distress in real time. For wild species, ecologists are moving away from lethal capture methods. Instead, they are setting up computer vision architectures and edge computing algorithms to monitor camera trap data, automatically identifying and tracking elusive, endangered solitary bees as they forage. Recognizing bees as an irreplaceable multi-billion-dollar infrastructure is the only way forward.